Hi there, in this video we are tackling LeetCode problem number 153. Find minimum in rotated sorted array. It is a classic medium-level problem that is essential for coding interviews and demonstrates the power of binary search beyond simple sorted arrays. This problem teaches you about divide and conquer, handling sorted arrays, and how to efficiently narrow down a search space to find the solution in logarithmic time. It also shows how small tweaks in comparison logic can lead to big improvements in efficiency. The minimum in rotated sorted array appears in many applications, from system optimization to searching in partially sorted datasets. So, let's dive in and see how we can solve this problem efficiently. Let's start by understanding the problem statement. We are given an array of length n that was originally sorted in ascending order, but then it was rotated between 1 and n times. For instance, suppose we start with our array nums with the values 0, 1, 2, 4, 5, 6, 7. Depending on how many times it is rotated, the array could take on several different forms. If it was rotated 4 times, it might become 4, 5, 6, 7, 0, 1, 2. Notice how the last 4 elements moved to the front. On the other hand, if it was rotated 7 times, which is effectively the same as rotating it 0 times, since the array has 7 elements, then it would remain 0, 1, 2, 4, 5, 6, 7. So, given the sorted, rotated array nums of unique elements, our task is to return the minimum element of this array. And here is the challenge. We must write an algorithm that runs in big O of log n time. That immediately hints that we will need to use binary search or a similar logarithmic approach, because a simple linear scan just won't be efficient enough. Now let's look at the constraints to understand what we are working with. First, n equals nums.length, meaning the variable n represents the size of our array. The array length is between 1 and 5,000 elements, so we are dealing with moderately sized inputs. Each number in the array can range from -5,000 to +5,000, which means we need to handle both positive and negative integers. And crucially, all the integers of nums are unique, no duplicates to worry about. Finally, nums is sorted and rotated between 1 and n times, which is the key characteristic that makes this problem interesting. So, with those constraints in mind, let's walk through our first example to make things concrete. We have nums as an array containing the elements 3, 4, 5, 1, 2, and the expected output is 1. Now, why is that? Let's break it down. The original array was 1, 2, 3, 4, 5. Which was a perfectly sorted array in ascending order. This array was then rotated 3 times. After rotation, the smallest element 1 is at index 3, that is, the 4th position. So the minimum element we need to return is 1. Now here is our second example. Nums is an array containing the elements 4, 5, 6, 7, 0, 1, 2. And the output is 0. Let's see why. The original array was 0, 1, 2, 4, 5, 6, 7, and it was rotated 4 times. After the rotation, the minimum element 0 ended up near the end of the array. Also notice how there was a clear break in the sequence. The numbers go up from 4 to 7, and then suddenly drop to 0. This drop point is where the rotation happened, and right after that drop is our minimum element. And here is our third example. Nums is an array containing the elements 11, 13, 15, 17, and the output is 11. Now, the explanation here is interesting. The original array was 11, 13, 15, and 17, and it was rotated 4 times. But since there are exactly 4 elements, rotating it 4 times brings it back to its original position. So the array looks like it was never rotated at all. In this case, when there is no apparent rotation, the minimum element is simply the first element, which is 11. So this is an important edge case to keep in mind. So now that we have seen the examples, let's explore the solution approaches. We will look at 2 main methods. First, we will examine the brute force linear scan approach, which is straightforward but does not meet the big O of log n requirement. Then we will dive into the binary search approach, which is the optimal solution that satisfies the time complexity constraint. Alright, let's kick things off with the brute force approach using a linear scan. The idea here is super simple. We are just going to walk through the array from start to finish and keep an eye out for the smallest number we have seen. By the time we hit the end, our smallest number will be the minimum of the whole array. Straightforward, right? To see this in action, let's walk through an example. Imagine our array with the values 7, 10, minus 10, minus 5, 0, 2, 4. Our goal is to find the minimum value hiding in there. So first, let's just visualize our array with its indices so we are all on the same page. We have 7 at index 0, 10 at index 1, minus 10 at index 2, and so on. To track the minimum value, we will create a variable called min value. We will initialize it to positive infinity or just a really big number. This ensures that the very first element we look at is guaranteed to be smaller. Now, let's start our journey through the array. We will use a pointer I to step through each element starting at index 0. Our pointer I is at index 0, pointing to the number 7. So the question is 7 less than our current min value of infinity? Of course. So we update min value to 7. Our current champion is 7. Next, we slide our pointer I over to index 1, which has the number 10. Is 10 smaller than our current champ? Nope. So min value stays right where it is. Let's move I to index 2. Now this is where it gets interesting. The number is minus 10. Is minus 10 less than 7? Absolutely. So we have a new champion. We update min value to minus 10. Onward to index 3, the pointer I is now on minus 5. Let's compare. Is minus 5 less than our current min value of minus 10? No, it is actually bigger. So min value remains untouched at minus 10. We repeat this for the rest of the elements 0, 2, and 4. None are smaller than minus 10, so our champ remains unbeaten. And that's it. We have looked at every element, and the final minimum value is minus 10. For the code implementation of this solution, we begin by defining the method signature. This method is called findMin, which takes an integer array nums as a parameter and returns an integer representing the minimum value. Inside the method, we first set min value to integer.maxValue. That way, any real element from the array will definitely be smaller and can replace it. Next, we loop through the array using a simple for loop, starting I at 0 and running while I is less than nums.length. Inside the loop, we check if the current element, nums at the index of I, is smaller than our min value. If it is, we update min value to this new smaller value. Once the loop finishes and we have checked every element, we just return min value. That is our smallest number in the entire array. As for the time complexity, we iterate through the array once, visiting each element exactly one time. This gives us big O of n time complexity, where n is the length of the array. The space complexity is big O of 1 because we only use a constant amount of extra space, just the variables I and min value. We don't use any data structures that grow with the input size. So, while this approach works and is very easy to understand, it not only fails to meet the big O of log n requirement, but also does not take advantage of a crucial property. Our array is sorted and rotated. Instead, it treats the array as if it were completely unsorted. So let's now look at an alternative linear solution, which you could also think of as a brute force approach that does make use of this structure by finding the rotation point. To understand this better, let's first visualize what a normal sorted array looks like. Imagine we have the array nums with the values -10, -5, 0, 2, 4, 7, 10. If we plot these values on a graph with indices on the x-axis and values on the y-axis, we can see the array elements visually. We have -10 at index 0, -5 at index 1, 0 at index 2, 2 at index 3, 4 at index 4, 7 at index 5, and 10 at index 6. Now, did you notice the pattern? The line connecting these points is continuously increasing from left to right. This is the key characteristic of a properly sorted array in ascending order. Every element is greater than or equal to the previous one. Now let's see what happens when we rotate this array. Consider the array nums with the values 7, 10, -10, -5, 0, 2, 4. Let's plot this on the same graph. We have 7 at index 0, 10 at index 1, -10 at index 2, and so on. Now notice what happened. The graph shows two distinct sections. From index 0 to index 1, the values are increasing. This is an increasing section. But then, from index 1 to index 2, there is a dramatic drop from 10 down to -10. This is a decreasing section, and it only happens at the rotation point. This drop is a key insight. In a rotated, sorted array, there is exactly one place where a larger number is immediately followed by a smaller number. We call the larger number the pivot element. In our example, 10 is the pivot element because it is followed by -10, which is smaller. And the element right after the pivot, in this case -10, is always the minimum element of the entire array. This is because the array was originally sorted, and the rotation just moved some elements from the end to the beginning. The minimum element is the first element of the original sorted array, which now appears right after the rotation point. Alright, let's see this approach in action with a visual example. We will use our same array with the values 7, 10, -10, -5, 0, 2, 4. With its indices from 0 to 6. Our game plan now is very simple. We are going to scan through the array looking for that one spot where a number is bigger than the one that comes right after it. That spot is our rotation point, and the element immediately following it will be our minimum. Let's start our pointer I at index 0, which is pointing to the number 7. We also need to peek at the next element at I plus 1, which is 10. Now comes the big question. Is 7 greater than 10? Nope. Since 7 is less than 10, the sequence is still increasing, just like a normal sorted array. This is not the break we are looking for, so we keep going. We slide I forward to index 1, which is now pointing to 10. That means I plus 1 is at index 2, pointing to -10. Okay, let's compare. Is 10 greater than -10? Yes, absolutely. And that's it. We have found the break. This is that rotation point where the array's sorted order is interrupted by that huge drop from 10 down to -10. And the element right after this break, the -10 at index 2, has to be our minimum value. Easy, right? So, for its code implementation, First, we handle the same edge case. If the array has only one element, there is no rotation to worry about. That single element is both the minimum and maximum. So we check if nums.length is 1 and return nums at the index of 0. Next, we iterate through the array to find the rotation point. We use a for loop with I from 0 up to nums.length minus 1. We stop at length minus 1 because we will compare each element with the next one, and we don't want to go out of bounds. Inside the loop, we check for the rotation point where the current element is greater than the next one. If nums at the index of I is greater than nums at the index of I plus 1, we have found the break in the sequence. The next element, nums at the index of I plus 1, is guaranteed to be the minimum, so we return it immediately. Finally, if the loop finishes without finding a rotation point, the array was not rotated, or it was rotated a full n times, bringing it back to the original order. In that case, the first element, nums at the index of 0, is the minimum, so we return it. As for the time complexity, this approach also runs in big O of n time because we potentially need to scan through the entire array to find the rotation point. The space complexity is big O of 1 as we only use a constant amount of extra space. So, while this rotation point approach is more elegant than tracking the minimum, it still does not meet the big O of log n requirement. For that, we need binary search. So let's now explore the optimal solution using binary search. But before we dive into applying it to our sorted array problem, let's make sure we understand how binary search works in general. Binary search is an efficient algorithm that finds a target value in a sorted array by repeatedly comparing the target with the middle element and eliminating half of the remaining elements with each comparison. Now here is how it works. If the target equals the middle element, it is found. If the target is smaller, the algorithm searches the left half. If the target is larger, it searches the right half. This process continues until the target is found or the search space is exhausted. This achieves a time complexity of big O of log n, which makes it exponentially faster than linear search. However, it requires pre-sorted data to work correctly. Let's see an illustration of how binary search works. Imagine we have an array nums with these values, and we are searching for target which equals 25. Let's visualize our array with its indices. We have 5 at index 0, 12 at index 1, 18 at index 2, and so on up to 87 at index 12. To perform binary search, we use 2 pointers. The left pointer starts at the very beginning of the array at index 0, and the right pointer starts at the end of the array at index 12. These pointers define our current search space. Next, we calculate the middle index. The mid pointer is at index 6, which points to the value 44. We calculate mid as left plus right by 2, which is 0 plus 12 by 12, which equals 6. Now we compare the middle value with our target. Is 44 equal to 25? Nope. Is 44 greater than 25? Yes, 44 is larger. This tells us something important. Since the array is sorted, our target value of 25 must be somewhere in the left half of the array, because all values to the right of 44 will be even larger. So we eliminate the right half of the array by moving the right pointer to the left. We set right to mid minus 1, which is index 5. And now our search space is only the left half. We then recalculate the mid pointer. Now mid is at index 2, pointing to the value 18. We calculate mid as 0 plus 5 by 2, which equals 2, using integer division. We then compare. Is 18 equal to 25? No, Is 18 less than 25? Yes. That means our target must be in the right half of the current search space. So we move the left pointer to mid plus 1, which is index 3. Now let's recalculate mid. The mid pointer is at index 4, pointing to 31. We compare. Is 31 equal to 25? No. Is 31 greater than 25? Yes. So our target must be in the left half. So we move the right pointer to mid minus 1, which is index 3. At this point, both the left and right pointers are at index 3. Let's recalculate mid. So 3 plus 3 by 2 equals 3. The mid pointer is also at index 3, pointing to 25. We compare. Is 25 equal to 25? Yes. This time we get a perfect match. We found our target at index 3. So this is the power of binary search. We found our target in just a few comparisons instead of potentially checking every single element. This in fact is a standalone LeetCode problem number 706, binary search. So now that we understand how binary search works on a regular sorted array, let's see how we can adapt it for our rotated sorted array problem. Alright, let's walk through a detailed example using a rotated array with these values. Our goal is to find the minimum element in the most efficient way possible. First, let's visualize our array with its indices so we can keep track of everything. We have 5 at index 0, 7 at index 1, all the way up to 2 at index 9. We will start by setting up 2 pointers. The left pointer begins at index 0 and the right pointer starts at the very end of the array at index 9. Let's now find the middle. We will calculate our mid pointer, which lands on index 4, pointing to the value 15. We get this by taking 0 plus 9 by 2, which gives us 4 with integer division. Now here is where the magic happens. Instead of a normal binary search, we are going to compare the value at mid with the value at the right pointer. So, is 15 greater than 2? Yes, it is. Now what does this tell us? In a truly sorted, non-rotated array, the middle element would always be less than or equal to the last element. But here, 15 is greater than the last element, which means our mid lies in the larger half of the original sorted array. Since the array was sorted and then rotated, this break in the order tells us that the smallest element and therefore the true starting point of the array must be somewhere to the right of mid. Now because we know the minimum is on the right side, we can completely eliminate the left half. We do this by moving our left pointer to mid plus 1, which is index 5. Our new search space is now from index 5 to 9. So, time for another round. Let's recalculate mid for our new search space. So 5 plus 9 by 2 gives us 7. So our mid pointer is now at index 7, pointing to the value minus 4. Alright, let's compare nums at the index of mid with nums at the index of right. Is minus 4 greater than 2? Nope, it is less. Now what does this mean? When the middle element is smaller than the rightmost element, it tells us that the entire section from mid to right is already sorted properly. In other words, there is no rotation break in this part of the array. This means the minimum element could either be our current mid value or somewhere to its left, because the rotation point where the order actually breaks must lie before mid and not within the already sorted half. So we shrink our search space by moving the right pointer to mid. Notice we don't do mid minus 1, because the mid itself is a potential candidate for the minimum. Our search space is now from index 5 to 7. Let's calculate mid again. So 5 plus 7 by 2 gives us 6. Our mid pointer is now at index 6, pointing to the value -7. Now we compare nums at the index of mid with our new nums at the index of right. Is -7 greater than -4? No, it is smaller. Since nums at the index of mid is less than nums at the index of right, we know this section is sorted, and the minimum must be at mid or to its left. So we move the right pointer to mid, which is index 6. Our search space has shrunk to just indices 5 and 6. So let's calculate mid one last time. 5 plus 6 by 2 gives us 5. Our mid pointer is at index 5, pointing to the value 20. We compare nums at the index of mid with nums at the index of right. Is 20 greater than -7? Yes, it is. Because nums at the index of mid is greater, we know the minimum must be to the right of mid. So we move our left pointer to mid plus 1, which is index 6. And look at that. Our left and right pointers have finally converged. Both are now at index 6. When the pointers meet, our search is complete. We have found our answer. The minimum element is at this position, which is -7. So we simply return nums at the index of left or nums at the index of right, since they are the same now. And that gives us our final result. For the code implementation of this solution, we start by defining the same method signature as before. First, we initialize 2 pointers for the binary search. Left at 0 pointing to the start of the array, and right at nums.length -1, pointing to the last element. These define our initial search space. Next, we set up the binary search loop. We use a while loop that continues as long as left is less than right. Once left equals right, we have found the minimum element and can exit the loop. Inside the loop, we calculate the midpoint using left plus right minus left by 2. This approach avoids potential integer overflow that could occur with left plus right by 2. Now comes the key decision, determining which half of the array to search. So we compare nums at the index of mid with nums at the index of right. If nums at the index of mid is greater than nums at the index of right, the minimum must be in the right half. So we move left to mid plus 1, safely excluding mid since it cannot be the minimum. Otherwise, if nums at the index of mid is less than equals nums at the index of right, the minimum could be at mid or in the left half. So in this case, we move right to mid, not mid minus 1, to keep mid in the search space. Finally, when the loop ends, both left and right points to the same index. That is the minimum element. We return nums at the index of left or nums at the index of right, since they are the same. As for the time complexity, this solution runs in big O of log n time, where n is the length of the array. With each comparison, we eliminate half of the remaining search space, which is the hallmark of logarithmic time complexity. This is a massive improvement over the big O of n linear approaches we discussed earlier. The space complexity is big O of 1 because we only use a constant amount of extra space, just the 3 integer variables, left, right, and mid. We don't use any data structures that grow with the input size. So, to summarize, we explored 2 main approaches to the find minimum in rotated sorted array problem. The first was the linear scan, which is simple and intuitive, running in big O of n time and big O of 1 space. It works by either tracking the minimum during iteration or finding the rotation point where nums at the index of I is greater than nums at the index of I plus 1. But it is not very efficient. The second was the binary search approach, the optimal big O of log n solution with big O of 1 space. By comparing the middle element with the rightmost element, we can tell which half contains the minimum and ignore the other half. This is the gold standard method that meets the problem's efficiency goal. And with that, let's wrap up this lecture here, and I will see you in the next one.